This conference will now be recorded.
All right, Ron, have at it.
Thanks, Bradley. Hi, everybody. This is Ron Lutzenheiser. I'm a geotechnical engineer with Geocon, and I'm also the current Capital Branch president. Wanted to thank everybody for attending our meeting this month. I know we all want to get back to in-person meetings as quickly as possible, but given the coronavirus situation, we are still planning to hold our lunch meetings virtually for the foreseeable future, and we are very glad that you decided to join us for today's presentation. I have a couple of quick announcements to make. The ASCE Capital Branch, we are going to be having our branch and section officer elections in the near future. At the branch level, we still have one position that's unfilled. So if anybody wants to volunteer to help keep the branch moving forward, this would be a great opportunity. If you have any desire or anybody that you want to kind of voluntold to participate, you can contact Bradley Waldrop or myself if you have any questions on that. Second announcement is that the COVID-19 Virtual STEM Fair, which is a student-led online science fair, it's designed to counteract the lack of academic activities during the global pandemic and help rekindle a passion for STEM during our socially distanced times. Students in 6th through 12th grades will research, design, and present a project for an opportunity to win cash prizes. The goal is to encourage 200 to 500 students in the Sacramento region to show off their STEM skills through either a research project or a physical project. They are currently looking for judges. If you would like to volunteer for help, please let me know, and we can put you in touch with the committee for that as well. The third announcement is each year, the ASCE Sacramento section recognizes individuals for outstanding achievements or leadership in civil engineering, or who, through their work, support and advance the profession. If you know someone who has gone above and beyond the call of duty for civil engineering this year, this is your chance to publicly recognize that individual by nominating them for a 2020 ASCE Individual Award. You can nominate someone online at the ASCE Region 9 Awards website, or you can contact Megan Leroy for more information. I believe there's also going to be a link on our Capital Branch website regarding this as well. And the last announcement is that the ASCE YMF group is having a virtual presentation on contingency engineering, construction in pestilence and war. It will be on this Friday, July 30th at 6:30 p.m. And we will be sending out an email with a flyer attached, so please watch for that as well. Sorry about that, my home phone went off. Okay, now that all those distractions are done, I'm gonna introduce Adam Killinger, who is our presenter today. He is GeoPier's region engineer in Northern and Central California. Adam has over 15 years of geotechnical consulting experience prior to joining GeoPier, who is a specialized design build ground improvement company. He completed his BS in civil engineering and geotechnical engineering at Chico State, go Wildcat, and received his MS in geotechnical engineering for Sac State. I guess that deserves a singer's up as well, right, Adam?
That's right.
Yeah. So Adam has experience in business development, project management, ground improvement design, and construction support. When Adam's not working, he enjoys traveling and spending time with his friends and family. His presentation will provide a brief description of short pile plate slope repair methods. All right, Adam, take it away.
All right, thank you, Ron and Bradley. Great to see the branch doing so well. It's great to be back and presenting. I am a past president of the Capital Branch, as well as Central Valley Branch, and a couple other things, as I'm sure many of you have done your tours of duty in ASCE. So that's good. Let's keep it going. Glad to see that the branch is in great hands. As Ron indicated, I am the region engineer for Northern and Central California. I handle ground improvement. Typically, these rammed aggregate piers is what GeoPier is known for. That's actually a phrase that is trademarked by GeoPier, but is frequently used elsewhere. and that's my territory. Typically, the Bay Area, South Bay, Sacramento are kind of the hot spots, but Central Valley certainly has its applications also. And yeah, as I said, mostly we do rammed aggregate piers, but I'm going to talk about slope stability today and the application of rammed aggregate piers for slope stability, as well as our SRT technology, which stands for slope reinforcement technology. So with that, there we go. I guess my normal controls weren't working. It's froze up. All right. So as we go through this, if you could just kind of keep in mind, what are the challenges you have with slope improvement projects? Whether it be from a project management standpoint, the technical challenges, what really irks you when you have to, you know, what challenges a project and raises your blood pressure as we go through this, and hopefully we can help find some solutions. So this is the kind of thing, geotechnical engineer. I realize that this is not just a geotechnical group, but I'm assuming everyone that's on this call that is a civil engineer has had at least one or two soils classes. And you can see here from a slope stability standpoint, which would have been at least a module in one of those courses, you can see some slope creep there on the upper right, some levee instability. Shoulder failures are a common one, or a deep-seated slide. And that's where our rammed aggregate piers would come into a slope stability situation. The rest of them would probably more of the SRT. So for the deeper slides, we're going to use that wrap technology. And you see there on the top for slides greater than about 15 feet. For shallow, modeled more as infinite slides, we would, you know, slides that are less than 15 feet, we can apply the SRT technology. So let's start with the conventional wrap technology for slope improvement. So just a refresher for those of you not practicing in geotech, what is global or slope stability? So we have some driving forces at driving the slope down in a deep-seated or a global instability. We're going to divide that by the resisting moments divided by the driving moments is what is defined as the factor safety of a slope stability. Excuse me, I had that reversed initially, but this is the general concept and the problem. So driving forces can be external load, surcharges to the top of a slope, seepage forces with water, overburden soil inside the critical surface. So the driving forces are what's known as the slices, driving on the top side of the slope or pushing down on the resisting forces of the slices of soil on the bottom side of the slope. And then what you have for resistance, unless you're going to have some kind of a mechanical connection, say a tieback wall or some kind of connection to the other side of the sliding surface, it's simply the shear strength of the soils in the resisting side of it, the toe of the slope. So this is a typical slope W model, what it might look like. Shearing failure, you see the slices there I mentioned. On the right side would be the driving side, the resisting side on the left. And if we put in a rammed aggregate pier, the wrap area at the toe of the slope to help resist the slices from above from sliding down, this is what the model would look like. So by putting the wraps in, what we're doing is we're increasing that shear strength, so that and creating a composite shear strength. So the rammed aggregate piers would typically have a phi value of 50 degrees and a 0 cohesion intercept. So again, for the non-geotechs out there, just a refresher, there are two types of strength parameters typically that we're looking at for slope stability projects. And that's going to be the phi angle of the soil, which is the internal friction angle, and the cohesion is how sticky is that soil to stick together. So you add those together and you get your composite envelope. So if we are able to put in, say this is a constructed embankment with some soft foundation soils, we can come in and put our piers in if the modeling that shows that the factor of safety is insufficient. So really this becomes a weighted average of the matrix soils of the foundation material and the strength of the wraps. So what's important to understand here is the R sub A, which is area replacement coverage, which is area replacement ratio. So it's basically just the percent area of the piers compared to the whole system. So the piers divided by the footprint of the sliding area. And then we're going to look at the composite C, the cohesion we talked about, and just take the area replacement ratio and take the weighted average. Same thing for the fee angle. So for an example here, if we took the area replacement ratio of say 20%, that means of all the area that we're supporting in our model there in the wrap zone in the model, is 20% of that is going to be in plan view, is going to be a rammed aggregate pier. Let's see, the matrix soil, C sub M is 500 PSF. Again, and let's say the fee angle of the clay is 0. And the fee angle, as said before, is 50 degrees for the geopier. Taking that, where the C composite drops, the cohesion is going to drop down a little bit, but we're going to pump up the fee angle to 13.4 from 0. And that's a huge benefit for those of you that have run models out there. I think you would agree. So that's going to stabilize the slope and increase the factor of safety. But there's something else going on here. Stress concentrations for the stiff rammed aggregate pier elements. So if we had a confining layer, a stiff layer or bedrock we were tying our piers into, in other words, the global stability would not, I guess a better way to put this, the critical slip plane in a soft soil that goes down 100 feet and our piers are say 30 feet, how we're going to be improving the factor of safety is pushing that slip plane deeper. So Mother Nature has a way of finding the path of least resistance. Well, if we're confined by that and our piers can tag into a dense layer or bedrock, then what's going to happen is our structural engineering friends would tell us that stiffer elements tend to attract more stress. And that's exactly the concept that is happening here. So should this be our condition, we can actually account for that with an R sub S. Now that's the ratio of the stiffness of the pier to the soil. Now for a completely rigid element, like in a rigid inclusion, conceivably the stiffness ratio is the ratio of the stiffness of the element to the stiffness of the matrix soil. But this is not that case. What we have here is a flexible condition, so that really the R sub S values are limited to 1 to 5. Whereas if it were just the ratio of the element to the matrix soil, it would be anywhere from 10 to 40 or 10 to 50. So that's important. It requires a little engineering judgment on this, especially as it relates to the profile. But there's a lot of alphabet here, but the important thing to recognize is this is just a weighted average, as I said before, with the stiffness ratio weighted into each element. So just for an example, if we were to look at this, back to area replacement of 20% and R sub S value of 3, using the same matrix soils with no wrap at all, no rammed aggregate pier, we're going to have a C of 500 and a phi of 0. That's not going to be the strongest slope. Neglecting stress concentrations, we're going to be at 400 and 13.4 as previously stated. And with the concentrations, we're going to drop our cohesion down to 286, but bump our phi all the way up to 27.1. So that's a huge advantage. And this is borne out in a number of papers. It's not a unique concept, but it's one that for the appropriate profile, soil profile and conditions can be used. So here's an example. How are we doing on time here? It looks like we're doing fine. In Louisiana, Crotch Springs, US 71 slope stabilization. Here's a project out in the bayou for where they put in added some fill on an embankment, and it destabilized the slope as they decided to raise grade for this bridge crossing. Here's kind of a look at where the slope was failing towards the watershed there. You can see where that scarp was intersecting the road as it degraded in the previous picture. And notice the 2 inclinometers there. So here's the borings, the profile. Let's see the clay fill they added, and the instability of the upslope and downslope. So a classic movement there. So like any slope stability problem, typically you're going to start with back calculating the strength parameters and the factors to get to a factor safety 1 if it's a failed slope or on the verge of failing. And that's what we did here, as you can see. So nothing new. And then we added the wrap area around the shoulder at the toe of that slope. And you can see the parameters up top using the formulas and the analysis we just went through. And was able to bump this up to almost a 1.6, but greater than a 1.5. Here's what the plan looks like for all the wraps that went in. You can see the toe of the slope there, the creek and the bridge. Just kind of brought that around and increased that, again, the resisting moment of the system to increase that factor of safety. And this is just a quick video here to help illustrate some of the technology that we used here. But whoa, that's loud. Sorry about that. I don't know if I blasted everyone's ears. This is showing just a classic drill and fill technique that we developed. We have a lot more tools than this for whatever application it is, whether it be, again, settlement control is by far the main reason people use geopiers. But for this talk, this is the technology they use to increase the stiffness of the soils at the toe of the slope, and again, increasing those moments. You notice the excavator rolls back on a heel of the excavator, and that's to get more reaction. But the concept is to extract soil from a hole here, put in different lifts. We're going to punch in a bottom bulb here to get a working platform, usually an open or closed graded or open graded material in the bottom, and then goes well graded all the way up to directly beneath the foundations or stiffening the slope. That's the general concept. So there's a cross section of where the piers went in. You can see how we arrested that slip plane, the critical slip plane, and improved that factor of safety. And this is what it looked like for the actual construction of this bridge. And piers in, repairing the road. We monitored it for 3 months and got the overlap they were looking for displacement. So that is, again, rammed aggregate piers are typically used for settlement control, but we can help you out with the deeper slides. Like I said, I think the mechanics are pretty clear on that. Tried to not get too deep in the details there but if any of the geotechs out there would like to have a conversation about some of the stuff, I'd be happy to come by your office once we can, and we can chat about it, or just give me a call. All right, so SRT, we're going to move into the slope reinforcement technology. So a lot of the challenges that we've been able to use with SRT is it's a surgical approach, if you will. There's a lower environmental impact because it's not a regrade situation. We're moving less earth. We can get on some fairly steep slopes, so where other equipment may not be able to, again, without massive earth moving and perhaps some retaining walls for the safety of construction. or tieback walls. The cost is typically it's quite reasonable in that regard. Maybe not as reasonable as just pushing the soil up the hill again, but that's just kind of putting a band-aid on a slope stability project. It becomes an annual maintenance issue. So yeah, it reduces the amount of future maintenance on a particular slope as well. So all these are things where an SRT system can help you and your owners. This is the general concept. You can see that we're going to take advantage of soil arching. There in the lower right corner, each row is staggered about 4 feet on center to arch between the plate piles ahead of it and below it, and or upslope from it. And the idea is to drag up some of that shear strength from the beneath the slip plane to reinforce the soils above. And it's actually, so it's a mechanical interlock system. I wouldn't consider this necessarily ground improvement as much as ground reinforcement. We're just stitching this thing together. So this was developed, the research for it was laid out at UC Berkeley. Richard Short was a big part of that. He got the original patent on this prior to GeoPier purchasing it from him. And he did a lot of great work with UC Berkeley and their research students to kind of hash all this out and come up to where we are at this point. But this is a great example. You can see here the soil arching I had mentioned between the plate piles being 4 feet apart there and holding back the, you can see where the slope had failed beneath the lowest row of plate piles. So it's a great illustration. And also here's, they ran 4,000 gallons of water in along a slip plane, and the slope worked fine. Once they extracted the plate piles, you see the result there at the bottom. This is what they look like. They're basically large speed signs, you might say. What you're not seeing there in the left picture is that plate pile is actually suspended with an excavator. So yeah, safety is always taken seriously, of course, and we consider the same. So it's yeah, that guy's not holding up all that steel. All right, and so it's a S3 by 5.7 section. You can see there. Here are the dimensions of a typical plate pile. We do account for moderate corrosion. So for moderate corrosion, 50-year lifespan, we throw in an extra 1/8 inch of steel as just being sacrificial. And the lengths will vary 6 to about 22 feet. After that, they get a little too unwieldy, even with the excavator holding it to get those guys in place. And it starts to be perhaps more economical to look at a different system. So typically, well, any slope, you know, if you've got a slip plane with some organics, maybe even a flatter than 3-to-1 slope becomes unstable, we can certainly help with that. But usually a 3-to-1 slope is pretty stable. So for this slide, it's 3-to-1 to 1-to-1, so about a 45 degrees. We've even done some slopes a little steeper than a 1-to-1. You have to start getting a little tricky with yo-yoing equipment off the side of the slope. We can certainly do that, but it slows us down a bit. So as I mentioned, slide thicknesses up to about 15 feet. And what we're looking for is, as I said, get these plate piles into a stronger layer below. So we're going to do that. We can't handle rock greater than about 3 inches in diameter. So cobblestone can be an issue if there's a significant portion of that. Soft rock is great. We can pre-drill or chamfer the edge of the plate pile at the bottom to help drive into it, and then that's obviously gives us excellent reaction and transfer some shear strength up to the slide. Hard rock would be a problem though, so it wouldn't be cost effective to actually do coring into a granite per se. So if you had to say a DG over a granite you were trying to hold back. But here's the beauty of it is for the civil designers out there, all this extra flat space to be able to work with. So just taking a 3-to-1 slope, and if you were to do the trigonometry here, you'd see that, you know, you pick up 1.375 times the height of the slope here to go from a 3-to-1 to a 1.5-to-1. So that can, depending on the height of the slope, that could be significant savings and creation of usable space. Here's what it looks going in. Just we can use a hydraulic hammer. They tap in pretty easily. We've done quite a few projects where we're throwing in lots of plate piles in a day. I mean, saving, so it's a major schedule savings for a project too. And this is using the vibratory. So how do we get these things in the ground for your project? I mean, that's the big question. If this is going to be a technology that can help you, there's a couple different ways we can bring these to you. One is depending on the nature of the project and the personnel around that project, is a general contractor or a maintenance crew can install these. That's typically going to be for less than 10 feet and a simple geometry, so no compound or three-dimensional analysis. What we would end up doing is going to our tables and coming up with a slightly conservative design to get these to provide to your owner, to you, and they can put these in directly. Or there's a design build process where we run through an iterative approach through L-pile and say slope W or slide, some kind of slope stability program, and we install through one of our pre-approved installers. So a couple different ways to go here, depending on whatever's easiest for the owner. All right, so direct channel, like I said, we would just need some information on the project as far as slip plane, soil parameters, geometry, and from there we could generate a design and provide those shop drawings to you for construction, and then installed by, as I said, general contractor, maintenance crew. If we look at the complex projects, this is our approach in the engineering behind the plate pile. We're going to look at a limited equilibrium analysis, just as we would in any other. We're going to back calculate along with the geotech on the project the parameters. We're going to go to those same tables and come up with a starting point for plate pile length and embedment and other dimensions. Then we're going to go to L-pile. L-pile, for those of you that aren't structural or geotechs, that's a lateral pile analysis by Insoft. And we're going to go to that, deflect these piles, assess the maximum bending moment hasn't been exceeded, and then come up with the shear resistance. Now that's the available shear resistance. That's key. We'll talk about that in a second. Then we'll go back to our limited equilibrium analysis, our slope or W or slide, insert our elements, check our factor safety, and see where we're at if that satisfies. If it doesn't, then we'll go deeper or tighten the spacing just to get to where we want. So this is the iterative approach for design on these. So as an example, here's a project. You can see the instability in the picture on the upper right there. So factor safety of 1 went in, some fill that was put in just before 2000, the year 2000. We came in, looked at the site, came up with this model, worked with the geotech of record to pull this together, and took our L-pile section that we talked about and put it into L-pile. We have that transition zone about 6 inches above and below the selected slide plane or the determined slide plane. And we're going to deflect that thing over about 1 inch. So it doesn't have to be 1 inch if that's generally what works for a typical slide. If we had, say, a paved road, we wouldn't want to go any more than that. We might actually tighten it up some just to keep the soil from moving. But we could also, if we were trying to hold back a slope, say above a road area where it would be fine for the soil to deflect a little bit more and then backfill in with just erosive material, on the tension crack, then that would be that'd be fine too. So, but the takeaway here is we're going to deflect this pile, and at that deflection, what is the available shear at that point? Because obviously the steel is going to put out quite a bit of shear. But in this case, we're getting about 1.6 kips with that deflection and geometry. So that's what we get to apply to every plate pile. And we're going to check that. In this case, the ultimate shear of the plate pile is 83, so we're typically never going to shear that. But the 1.6 we can apply to every plate pile, and the arching in the staggered array that's on the hillside to bring that shear back up to reinforce the soils, the sliding soils. So hopefully that makes sense to everybody. We'll check the bending moment. Good there. So again, for that deflection and geometry, looks like we're going to generate 26 kips of bending, well below the yield of the section. So now back to our model here. We'll put in these stiff elements, and vector safety came up to, again, almost to a 1.6, so above a 1.5. So I think we have a little bit of time here, so I could bounce around on these, but I think I'll just go through some examples. So here is a temporary excavation. Now, typically, you know, plate piles are used for permanent solutions, but in this case, we were able to come in and use them for on a 0.4 to 1, so really steep slope, and get to a factor safety of 1.2, which is fine typically for a construction situation. The alternative was an auger cast secant wall, which was quite pricey. Vibrations were a problem for the sheet pile wall, and GeoPier was able to provide the SRT for low vibrations and fast installation. So you can see the slope there, pretty steep. That was the model. And we went in and put these in Missouri. And as soon as we got these things in, we ended up with like a 200-year storm, and it just hit the site with a deluge. And you can see, oh, and here's you can see with the surcharge load, got the plate piles in. What you can see there in the right picture, which is quite interesting, the plate piles doing their job holding up this slope, and the erosion from the front side of the plate pile. So worked out great, worked like a top, as they say, and they were able to get this thing in and get this thing built in record time and way under budget. But the takeaway here is just the performance. We would never design a permanent solution for this steep of a slope with SRT, but it does show how it performs. This is an interesting project. This is a Caltrans I-5 at Highway 20 there in Williams. We put in a slope for Caltrans there, so a DOT job. We are in the Caltrans manual. I know that there are quite a few Caltrans people out there listening potentially. So this is a great project illustrating that. This got us in the manual. The need for the job was geometry constraints. So rather than the standard 3-to-1 DOT slope, could be on the left side of the slope there. Due to wetlands, they had to steepen that up to a 2-to-1. So we came in and installed 9,000 plate piles in 70 days. As I said, these things go in pretty quickly. 6 to 10 foot lengths, and saved about $3 million on the project, along about 1.5 miles of roadway. And that's what it looked like sometime after. Here's a power plant in New Madrid, Missouri. Levee stabilization there. You can see they were having some maintenance issues keeping this levee in spec with the geometry. Excuse me. And brought us in. The power plant was involved, so it really wasn't an option to have this thing breach. 1,500 plate piles in 12 days, saved about $1 million on that compared to the alternative. And it's a robust solution. It's a fix that's going to be there. You're not going to be out there with a scraper or grater tidying this thing up every year. So we're going to pin things back mechanically. Once the vegetation grows over the top, it's in place and set. And I mentioned vegetation. That's we're going to drive these things in 6 to 12 inches below the ground surface, so you don't have to worry about people stepping on them or cutting their feet on them. Once they're in place, you don't even know they're there. So here's a project, and this is actually fairly common for us to use SRT for. Is sliding or creeping slopes around pipelines. So in this particular job, we were able to come in and they were having all kinds of maintenance issues with the pipeline because of the moving slope. And this is in Kentucky, and you can imagine the strain and stress on a pipeline, especially if it's a lifeline for a creeping slope. So they've been fighting this thing for years with just a bunch of regrade. We were able to come in. You can see the 3 pipes there in the profile. Able to get some plate piles in to hold this thing in place, stitch the slope together, quit moving, and saved on all kinds of maintenance for the utility. There you can see the layout. 5.5 foot spacing, 19 rows, 10 foot long plate piles, 4 foot. So depending on which tier you're looking at. Again, the same process that we talked through as far as the design on these things, though. And there they were going in. I don't know why they tapped them in the way they did that way, but that's just the way the contractor decided to. He put them partially in and then retapped them. All right, here's an emergency repair in Memphis, Tennessee. This is, I think, the only hill in Memphis, as I understand it. And we had a situation where this came down after a large rainstorm. They were concerned it took out a little bit of road. It wasn't that big of a deal, or at least it doesn't appear that way to me. But again, for the only hill in Memphis, they were pretty excited about it. It was on the news. We were out there just a couple of days later and got this thing fixed. Again, went in and tapped these things in, fixed the problem. And one advantage, this is probably a good opportunity to mention this, is compaction. The plate piles, the way they operate and the theory behind it, we don't need to meet compaction, as it can be challenging with putting sliver fills on a slope. So we put the plate piles in, we get the interaction with the soil, with the initial movement, and everything locks in place. We just track walking the slope is sufficient as far as getting material back into geometry. So why SRT systems? We've touched upon these mostly along the way. They're fast and economical. Permits for more workable area, more flat area for the owner, to help tier some locations on the hillside. They're constructed with, just as you saw there, small to mid-size excavators. So we're not going to come in and blow up the site and scrape it and pull everything down. It's easy to respond to emergency repairs, so quick response. Minimal site disturbance. So here in California, the environmental impact is far less. It can be desirable depending on the project needs. And it's a high confidence engineered solution. It's robust, and it's not just putting the Band-Aid on, going out and pushing the soil up the hill again. So it's more about a final fix. So with that, this is my contact information. If anyone out there wants to take a screenshot of this, I would be more than happy to give your office or your group a presentation, either this presentation or one. The more commonly would be one of these technologies. So these, like I said, we have a lot of technologies. Slope stability is just one thing we touch. Far more commonly would be controlling settlement of structures. You see SRT bottom, second from the right, but we also have a geospike system, which is on the bottom right there, which is an amazing system for tracks falling out of alignment or excuse me, of settlement. So if anyone would like to talk to me about that, I can get them set up as well. So with that, I guess we'll open it up for any questions that anyone has.
All right, thank you very much, Adam. We have only a few questions that have come in during the presentation, but as you get to answering, we might have more. Ron Lutzenheiser actually asked, how deep do the plate piles have to be installed, and is there a typical depth below a slide plane or ratio of length above the slide plane versus below the slide plane? That's a sort of general guidance.
So it all depends. It's a great question, but it all depends on the strength of, or the lack of strength of the sliding soil versus the resisting strength of the soil below. So for example, if we had a soft rock situation, we wouldn't need to get into it very deep at all. If we only had, say, a 4 or 5 foot slide, we maybe just a few feet into that rock would be enough to stitch that slope together. If the resisting soil beneath is only marginally better than the sliding soil, then we're gonna have to go a lot deeper to make sure we get those things. We get the because remember, we got to deflect these things. We don't want them fence posting too much. So if we have to deflect them, we may have to go deeper just to get the reaction we need to make that mechanism work. So hopefully that answers his question.
Okay, cool. Brett is asking whether or not you guys had participated in the Santa Barbara landslides a few years ago.
Not to my knowledge.
Okay. And then a question that Russ and I have, we actually have a project that one of your solutions may work. We don't know. We're in the midst of working out some of that as we speak. But if we're having a tough time accessing the toe of a slide, and it's a fairly deep slide, is there a solution in there that allows us to install the wrap technology or maybe another one of your technologies a little bit further away from the toe of the slide and still be effective?
Well, that would come back down to the geometry of the slide. Okay. So we could put that wrap zone wherever we need to, as long as we're intercepting that critical slip plane.
Okay.
Then it would just be a matter of running the model to see how much we're helping.
Okay. And then as a matter of example to the rest of the folks that are on the call, yeah, I get that we're going to give you a call and try to include you. What kind of preliminary information do you need from us so that you're productive in a brainstorming session or a conceptual idea sort of back and forth? And how far in advance do we have to schedule something like that? Who would you like to see on a call like that?
Great question. Great question. So, I'll talk about slope stability first, and then also just throw out the more conventional GeoPier application for settlement. So for slope stability, what we're really looking for to come up with the final design is we're going to need to know slide depth. We're going to need to know desired factor of safety. We're going to need to work with the geotechnical engineer of record to work out the strength parameters of the soils both above and below the slip plane. And then lastly, the easy one is just the geometry. So those are the 4 things we need. So the topography of the slope, the depth of the slide, strength parameters, and whatever factor of safety is acceptable. Now for just GeoPiers, if you have a structure and you're looking to control settlement by getting away from deep foundations or having to remove a bunch of undocumented fill, what we would need is simply the soils report, the foundation layout, and the loads. Now you may not have the foundation layout for a structure, and this is kind of an aside here, I know, but what you what we could still run as feasibility and tell you how much bearing capacity we can provide for the given soil solution.
Perfect. And then Lee wrote in and sort of it looks more slope stability, general philosophy. And is there ever a case that the slide occurs and you would predict that there'd be no more sliding because the overburden is gone and now it's just resting?
Yeah, well, as putting on my old consulting hat and not design build, yeah, that would be, I guess the question popped up then is the new geometry configuration with the scarp and the spoiled soils at the toe, is that new geometry still functional for the owner and the facility? If the answer is yes, then yeah, do nothing is always an option for sure. Again, though, I'll segue that into saying the nice thing about this system is you don't have to worry about sliver fill compaction. We have blade on the small excavator, or the contractor could use that and just push everything back into position, tap in the plate piles, and up and running. So if geometry is a challenge, that's nice to have that option.
That's great. Well, I don't have any more questions. Ron, I think you're on.
Sounds good. Thanks, Bradley.
For sure.
And Adam, thank you very much for being with us today and giving your presentation. I know I got quite a bit out of it, and I hope others did as well. Want to let you know we'll be sending you a small token of our appreciation for your presentation today. Thank you.
Well, I really appreciate it. Yeah, thank you for your time, and it's great to be back with the Capital Branch, and great job. Look forward to future interaction.
Yeah, and hey, like I said, we still have one opening available on our ballot. So if you're, if you're interested.
Thank you much. I'll consider it.